The outline on slide 76 shows that we are now ready to compare results using the manual approaches. Let's remind ourselves about the model that we're considering. We have the latent class indicators, the distal outcomes, and the covariates. And one key question is, where in the Mplus output do we find the various results? And I like to summarize the parts of the results by using these causal arrows: the X to Y influence, the C to Y influence, and the X to C influence. So X to Y is what we're showing here on the right side of the figure. So that's in Mplus language Y on X, Y regressed on X. And with continuous Y, that's regular linear regression slopes that we find in the regular model results section. For categorical Y, we have added a special section, logistic regression odds ratio results. So that's in addition to the logits that we give in the regular model results section. For C influencing Y, that is C influencing Y up here, those arrows, what we're looking at are intercepts for Y or thresholds for Y. With continuous Y, these are the linear regression intercepts, that is the brackets for Y, which are shown in the regular model results section. With categorical Y, we're more interested in odds ratios in addition to the thresholds that are given in the regular model results section. So we have a special section on odds ratios for that. Finally then, X influencing C, so this part of the model, that's a C on X regression, which is a multinomial logistic regression. And in addition to the regular model results logits, we also give odds ratios for that. We're going to take an example showing in the output parts using BCH. On slide 78. So here we have X to Y results for final step of BCH. So at the top here, the top table, we're talking about Y1, which is continuous, and at the bottom, we're talking about Y2, which is binary. So what we have then is a regular regression, linear regression Y1 on the X's with their standard errors and the ratio of the two, and we see that all three of them, all three X's, have a significant influence on Y1. At the bottom of the table, we have Y2, the binary one, and here we're looking at the logistic regression odds ratio results, where we would then be interested in the odds ratios and their 95% confidence intervals, and whether or not the confidence interval covers 1. So here it doesn't, so X1 has a significant influence on Y2, and so does X2 and X3. Now, here, in this case, in this model, these regression slopes or odds ratios are the same for all classes because we have a class invariant Y on X regression specified in the model. If you look at the C to Y results, continuous Y, we have intercepts. So the effect of C on Y is captured by the intercept varying across classes, class 1, class 2, class 3. We don't have a regression Y on X language, but instead you see the effect of C on Y in these intercepts in the regular results section, model results section. C to Y results for categorical Y, we're going to focus on the bottom two sections of this table. We have Y2 and Y3, Y2 being binary, Y3 being polynomous, ordinal. So we compare class 1 to class 3, seeing if there's a significant effect on Y2 in terms of the odds ratios. And the odds ratio has confidence interval that does not cover 1, so latent class 1 compared to latent class 3 does indeed have a significant effect on Y2. For Y3, however, there's not a significant effect because the intervals cover 1, and we saw that earlier as well. So this is class 1 compared to class 3, class 2 compared to class 3. We have insignificance for Y2 as well as for Y3. So it's a class 1 that is the one that has most of the effect here on the distal outcomes. Going to slide 81 then. We have a regular C on X regression, C#1 on the 3-axis and C#2 on the 3-axis. C#3 slopes are fixed for identification purposes as usual. So here we find that X1 has a significant influence on the first class relative to the last. So does X2 and X3. But for class 2 versus class 3, there's not an effect by X1, but there's a significant effect by X2 and not a significant effect by X3. I think I said that right. All right. That's where we find the results. So now a reminder here on slide 82 about which approaches we have available with missing data on covariates. We have ML and numerical integration. We have Bayes. We have multiple imputation. And we have the combined imputation and final analysis possibility, which is available for all 3 methods, just like multiple imputation is. Slide 83. This is a bit of a technical think piece slide. Not incredibly important, but it's a good way of thinking about both analyses and simulations. So now, when we're going to compare the multi-step results across methods, what's the best basis for comparison? Well, the full model is what we want to consider with indicators, covariates, and distal outcomes. And we can get results for the full model in a couple of different ways. First of all, we have a correct full model that generated the distal.dat data set. I mean, that's typically unknown in real data, of course. Here we use the Monte Carlo simulation. The data generating model population command specifies the probability of missing data on X1 and X2 as functions of the non-missing X3 variable. And we show that in appendix slide 135, how we generated the data. So here we know the missing data mechanism. When X3 increases, the missingness on X1 and X2 increases. I think it's increasing, could be decreasing, but it's a function of X3. Now, the model, the analyzer generated the data, correctly specifies X1, X2, and X3, shown on slide 137. And those results agree. So that's treating the generated data as real data. So we can compare to that. Another comparison is the one-step analysis of the data generated by the model that we know is correct, but bringing x1, x2, and x3 into the model using with instead of the on that we have here, because the missing data mechanisms is unknown. So this is most close to the situation with real data. And the one-step analysis is motivated here because the true model follows the model used in the one-step. The one-step analysis does not have that distorting effect of distal outcomes or covariates due to how the data were generated. So we say x1, x3 with x1, x3 as we talked about earlier, and that's an approximation of the correct model, but one that more closely represents real data analysis. But a key comparison is with the class probabilities of the measurement model. Nevertheless, we're going to take a look at several model parameter estimates. One step with the integration is done this way, and it's very familiar to what we've seen before, so I'm not going to talk about it much. We use algorithm equals integration Monte Carlo, and we have x1, x3 with x1, x3, getting two-dimensional integration. On slide 85, we start the comparison of LCA class probabilities across different approaches. So on this first slide, 85, we're going to take a look at maximum likelihood estimation using integration. The first model we consider is the correct full model, that is the model that generated the data shown on slide 137, where we know the relationship between the x's. And here are the class probabilities. Turning to the one-step approach, we act as we would when we don't know the missing data mechanism, and we simply covary the x's with each other like this. And we get these class probabilities, and we see that there is a slight difference here and here, but not very much. So we can consider the one-step model to be the correct model here. Usually in simulations in the literature, the focus is on models where one step gives bias relative to the multi-step approaches. But here, while one step is actually a correct approach to which we can compare other approaches. So let's turn to a multi-step approach. First one is three-step, and we consider the measurement model here first. 0.263, close to that. 0.291, well, there's a bigger difference. 0.446 is also a bigger difference. So this model, one-step model, a full model, is correct, but the measurement model is only a part of that, and it would only be expected to give the same results when you have a very large sample where part of the model gets the same estimates as the full model if the model is fully correct, or if you had many different replications in a Monte Carlo study. So these differences are what you would expect in a single replication analysis, so to speak. So that explains that. But we're going to focus on the agreement between the first step and the last step. And you see here that we get fairly close, but not exactly spot on. But it's close enough, I would say. VCH cannot do integration, so let's see what two-step comes up with. First step measurement model, of course, that's the same values as for three-step, the same measurement model. And now the differences are also quite small, and I would say ignorable. Slide 86 then, let's take a look at Bayes, using Bayes in the last step. And the first step probabilities are the same as usual. And the last step then is a little bit, once again, a little bit different, but not far off. Two-step, similar behavior, similar but not the same. The 0.283 here for two-step. Disagrees a little bit more with 0.291. And then the ML that we used on the previous slide. So one could say that base does a little bit worse than ML in matching here for the second class. But it's hard to say from a single replication, that single data set. You need simulation studies to decide on that. Turning then to the multiple imputation using the combined approach. You have three-step here, same degree of discrepancy, not a lot, but a bit. And BCH, however, manages to nail it right on target here. So it does very well in this multiple imputation combined approach. Two-step, a little bit different once again. So that's the latent class probabilities, how they compare from the first to the last step. Now, if you look at other model parameters, and we have here the one step with integration. You have x to y here. That's a regression of y on x. C to y, changes in intercepts or odds ratios. And x to c. What we're going to take a look at is not the numbers per se, but significance. So we have asterisk where there is significant results. Now, on slide 88, we have the ML combined approach. And if you compare with the previous slide, there is non-significance here for this value, whereas we had significant for one step. And we actually have significance for other approaches. So here's BCH. BCH gets that significant. And so does two-step. Now, slide 89, going back to that, we have a non-significant value here for BCH, whereas it is significant for three-step and significant for two-step, and it was significant also for one-step. But by and large, one could say on slide 91 that the results differ somewhat across multi-step approaches, even for a model that is what I call largely correct. You know, we don't specify the missing data mechanism exactly correctly when we just correlate the y's, correlate the x's rather, bring them into the model, or do the multiple imputation. We don't take into account the correct missing data mechanism because we typically don't know what it is. But the differences are small, ignorable I would say, and do not, by and large, do not change significance of the estimates. And you have to keep in mind that these results are based on Monte Carlo generated data from a single replication. A literature summary of Monte Carlo studies with many replications, which is what you need, is to date, the summary to date is given in the statistical methodology section, showing that the choice of best multi-step approach depends on the circumstances, some of which are unknown and unknowable also. And I think that for any given data set, it may be warranted to study results from all the approaches and see which results do and do not hold up. With a combined approach, for instance, it's not hard to do all three analyses, all three multi-step approaches, and then see which results hold up and which don't.